existence and uniqueness theorem. Let R be a rectangular region in the xy plane defined by the closed interval AB and closed interval CD for x and y respectively that contains the point x0, y0 in its interior. If the function f of xy and the partial derivative of the f with respect to y are continuous on R, then there exists some interval I0 contained in the closed interval AB and a unique function y at x defined on I as 0. That is the solution of the initial value problem. dy by dx equals f of xy with the initial condition y at x0 equals y0. Differential equation in the normal form with the initial condition y at x0 equals y0. For an example, determine a region of the xy plane for which the given differential equation would have a unique solution, whose graph passes through a point x0, y0 in the region. This differential equation is already in the normal form, where f of xy is square root 4 minus y squared. We don't see x variable in this function f(xy), therefore x is defined everywhere, but the restriction is for y. Y cannot be any number less than 4 or between 4 and negative. Examples. Number 1. Determine a region of the xy plane for which the given differential equation would have a unique solution whose graph passes through a point x0, y0 in the region. Part A. dy by dx equals square root of 4 minus y squared. This differential equation is already in the normal form. Therefore, the function f of xy is square root of 4 minus y squared. We are going to find the region that this fxy is continuous. There is no x involving in this function. Therefore, x is defined everywhere, or it's continuous for any x value in the real number line. But for the restriction of the y, 4 minus y squared has to be greater than or equal to 0, or y squared minus 4 less than or equal to 0, factor completely. We have the critical numbers positive 2 and negative 2, but to satisfy this inequality, any value greater than 2 will give the product positive. Any value less than negative 2 which result the same thing, but any value between negative 2 and 2 will give the product less than or equal to 0. So that's the reason the function fxy continuous for the y value. So we said fxy is continuous on x negative infinity, positive infinity, and the y between negative 2 and positive 2, including the endpoints. Next part, we are going to check the partial derivative of the function f with respect to y. In this case, we are going to apply the chain rule. We have 1 over 2 quantity 4 minus y squared to the power negative 1/2 multiplied by negative 2y. Simplify a little bit. So we get negative y divided by square root of 4 minus y squared. Determine the region that the partial derivative of the f with respect to y continuous. Similar way, so we say the partial derivative of the f with respect to y is continuous on the open interval y greater than -2 less than +2, not including two endpoints, otherwise it's gonna be undefined. So fxy and the partial derivative of f with respect to y, both of them are continuous on the common interval y greater than -2 less than +2. And for all value or real number for x. Therefore, the region R is the region that y greater than -2 less than 2 contains a unique solution. Passing through a point x0, y0.